I wanted to say that for the past 2 months approximately, I've been crying myself to sleep every single night because this is the first time I do passwords.com when I'm actually not doing a talk myself. And that is because this year we had so many excellent submissions, and there are also backup speakers that will try to fit them into the schedule because we have synchronized completely with the rest of B-sides, as you've seen in the program, and there are breaks in here so that you will be able to get lunch and so on. And I don't really get the point of that. You can easily survive until Thursday, and we have passwords to discuss. So later today, and also the 1.5 hour breaks, I will insert at least one additional talk. I will put it out on Twitter. I will also announce it in here when I know who will be speaking and exactly when, but there will be some additional talks as well. So having said that, I'm going to introduce you to JP Omerson from Kudelski Security and his talk, What's Up Argon2? And I got to ask JP, is this going to be a lot of cryptography?
A lot of equations in math, so if you don't like math, please leave the room. No, just kidding.
Any kittens?
Sadly.
No kittens. Okay. Well, yeah.
I'm not.
So, no kittens. Yeah. No. So, let's give a small applause to.
I can dance, or all right. Hello. Good morning. So I'm happy to be here again. So I will talk about Argon2. So, who knows what Argon2 is? Oh, quite a few people. Who use Argon2? Come on. You're in the right room. So that's going to be a super short talk, like 20 minutes or so, but I want to bore you with the equations. You probably heard about the password hashing competition. So if you did not, you may have heard about the AES competition like 15 years ago, where the US government picked the AES standard by selecting it from a bunch of algorithms submitted by researchers. So that was the same kind of process that we ran between 2013 and 2015. So we got a group of people like software engineers, password crackers, cryptographers, and we asked the community to submit their designs, algorithms, their code. And we evaluated it. We tried to figure out how secure are the submissions, how fast, how serious. And so on in 2015, we decided that the winner would be Argon2. The hash function that I will present today. And so it's been about a year, and I will present what's been happening for this year. All right, so maybe besides the fact that we picked Argon2, which is the best password hash in the world, from my point of view, I think we also motivated researchers to care about password hashing. Because nobody really cared about research on passwords before. It was about cracking passwords. So that's nice, that's a fun topic, but you also need some different approach. Try to think about what's the optimal way to build a password hashing algorithm instead of just cracking MD5 SHA-1 for the rest of your life. So now we've got Argon2. Why did we pick it and not the others? There were plenty of very good submissions. So it's secure, but there were also some other secure submissions. It's one because we wanted people to use it. It's not an academic context, it's not a beauty contest. It's an engineering contest, and one of the criteria was usability and UX and user-friendliness. So it's pretty much simple. It's easy to use. I hope so. I'll hope to convince you that that's true. So who's behind? It's not me. It's some people from Luxembourg, some very well-established cryptographers. Alex Biryukov, who's been leading the lab for a couple of years now. Daniel Dinu and Dmitry Krovatovic, who is the lead designer of Argon2. All right. So how does this work? I have no math, no equations. First of all, you take your password, you take a salt, you take a bunch of parameters, and you hash everything using some cryptographic hash functions like a general purpose cryptographic hash. It happens to be based on Blake2, but you could use any hash function you want. So that you get a value called h. And what you're going to do, you're going to allocate a bunch of memory, a table of 2 dimensions, a bunch of rows, a bunch of columns. And the size will depend on the memory parameter that you choose. So if you want this table to be just 1 kilobyte, it will be 1 kilobyte, but you can make it up to 1 gig or even more. You can make it, I don't know, 10 terabytes if you like. So using your value h that depends on the password, so you can't determine h if you don't know the password, you will fill this huge table. You will fill the first column, the second column, the third column, and so on and so forth, but sequentially. So to fill the nth column, you need to know the column that comes before. So that's super simple. So how does it work? You have blocks in this table. So like I said, they will all depend on h, on the password. All right. So when you fill one column, it depends on the previous column, but it also depends on another block. I will explain later on what this means. And then you repeat it several times. You fill the table once, you fill it twice, how many times you want. So if you want the hash to be slower, you will fill the table more times. If you want it to be faster, you will fill it only once. So that's it. That's how it works. I try to make it simple, but you don't have all the details. You look up the specs if you want, like all the nasty details. All right, so there's two versions of Argon. Argon2D, D for dependent, and Argon2I for independent. In the previous slide, I remember that I said that when you fill this table, the value depends on another block in the table. So in Argon2D, this block will depend on the password. It will always be a different index. It will be a different address in memory if you have different passwords. In Argon2I, it's independent. So whatever password you choose, the address in the table will be the same for every block that you compute. So you see where I'm going. If you have a memory address that depends on the password, you've got memory access that depends on your secret. And if you can monitor the memory accesses, then it gives you some sidechain information on the password. So more precisely, it gives you information on the hash of the password, the small h value. And if you can figure out the full value of h or even a small part of it, it can allow you to crack passwords much, much faster. So the upshot here is that if in your threat model, if you care about sanctional attacks, about software sanctional attacks, you should pick Argon2D, where sanctional attacks, Argon2I, sorry, where sanctional attacks will not be relevant. So what's the advantage of Argon2D, the weakest one with respect to sanctional attacks, is that you get a better security against time memory trade-off attacks. I will talk about it a bit later. So now how fast it is, so it depends. It depends on your CPU, it depends on the parameters, it depends on a lot of things, but to give you an example, if you take Argon2D with 250 megs on a single core, it takes approximately of the order of 100 milliseconds. Argon2I with 1 gig of memory and 2 cores, it's about half a second. But you should not rely too much on this kind of estimate. You should run it yourself on your machine, on the platform where you will hash the password, and measure the timings and figure out which one is the best for your application. So what's the applications of Argon2? Well, not sure we need this slide. It's pretty much obvious. We need to store passwords, to derive keys from either passwords or any low entropy token, and as proofs of work. Obviously, there's already an altcoin that uses Argon2. Okay. So let's say you want to use it. The good news is that you don't have to implement it yourself. The code is already out there. We have a nice reference code in C, C989. It works on Linux, on any BSD, on Windows. You just download it, you clone it, make, and it gets you static library, shell library, and the command line utility that will let you benchmark Argon2 on your machine. So there's no patent, no strict IP. It's essentially public domain. Say C0 license. And we've got bindings for Python, Lua, Go, Java, all the usual languages. So it's been less than a year since we started this. It's based on the C++ code of the designers. We quickly figured out they were not using any real C++ features, so we turned it into C. It got pretty popular now. We've got more than 1,000 stars on GitHub, more than 400 commits, more than 90 pull requests, many issues too. So the code was quite, was not so good a year ago, but now it's much, much better. So now I can recommend you to use it. So I'd like to thank everyone who contributed to Argon2, Samuel, Dimitri, me and other guys. Some people even start to use it. Libsodium, which is maybe one of the best crypto libraries and one of my favorites. The default password hash in Libsodium is now Argon2. So thanks to Frank Denis for pushing this in Libsodium. There's a Debian package that provides you with a library and the command line utility to use Argon2 so that you don't have to build it yourself or to implement it yourself. So now the elephant in the room, why using Argon2 and not something else? So there's no simple and square, but I will only compare to script. So script is used to be the state-of-the-art password hash before we did this. But one of the reasons we did PhD is that we were not satisfied with script. So script is good. It kind of does the job. It uses a lot of memory. But if you ever try to use script, you know that it's not easy to use. You get a bunch of parameters, not very clear what they're doing. You can make it bigger. You can make it use more memory. But for instance, you don't have a time parameter that makes it slower without making bigger. That's inconvenient if you want to make it slower without using more memory. And like I said in Argon2, we have two versions. One data independent and one data dependent. So in script, you don't have data independent mode. That's another limitation. And finally, if you look at the algorithm itself, so it's pretty weird because you have a password hash script, but inside you're using another password hash, using ppkdf2 and the HMAC construction and SHA-256, and you also need a stream cipher. You need SLSA20. So you need a lot of stuff, a lot of code to debug, so it's not very elegant. Whereas in Argon2, it's much simpler. You just need the core function of Blake2, and that's it. Also, we've got, from my point of view, a more reliable security analysis of Argon2. So there's essentially 4 parts. The first one is how strong it is with respect to cryptanalytic attacks. Stuff like differential attacks that you have like on block ciphers or stream ciphers. So maybe last week someone told me, I don't want to recommend Argon2 because we gotta wait maybe another 2 or 5 years before we're confident that it's secure. I was like, well, it is Blake2. It iterates, Blake2 maybe, dozens of times. And even if it's only iterated 10 times, we don't know how to break it. And we're super confident that it's secure. So should really be the least of your worry, cryptanalysis. So I view it as security, not as performance, inefficiency on GPUs, ASIC, FPGAs. So what the Argon2 designers did, they tried to make the algorithm as fast as possible on your machine and as slow as possible on the bad guy's machine. So of course they did it when they did it, like last year. In 10 years it might be different. But what it means today is that it's optimized for the x86 architecture, for the recent microarchitectures where you have SIMD operations, and it exploits multi-core, multi-threading. You can ask Argon2 to use as many threads as you want. So if you have like 4 cores on your CPU, you may want to use the full 4 cores. And the point of using a lot of memory is obviously to make it much more expensive for the ASICs, for hardware circuits. All right. Side channel resistance. Like I said, it's only software side channels, mostly everything that's related to cache timing attacks. Argon2 so where the memory access are independent from the secrets. So it's time constant. It always takes the same number of operations to hash password. And the memory addresses are always the same, which means that it's secure against this kind of attack. And Argon2D is not. Okay. The last part, maybe the most interesting one from a researcher's point of view, not the easiest to understand, so I won't go into full details, but I will just summarize the 2 major papers that came out earlier this year. So the point of this kind of attack is to compute the hash function result by using less memory than intended by the design. So like if you say, okay, I want Argon2 to use 1 gig of memory, and if you can compute the result with just 1 meg, then something's really, really wrong. Okay, and same from time. So the first paper that came out is this one by a team from Stanford. So you probably know Dan Bonnet. They did very brilliant work from my point of view. They were like, okay, we have these guys playing with password hash functions. They don't know what they're doing. Okay, let's solve the problem. That's how I saw it. They got more than 50 pages of analysis. They got a new design called balloon hashing. And they showed, that was really surprising to us. They showed that you could compute for certain parameters the result of Argon2i by using 4 times less memory in some specific settings that were not the recommended settings we had in the paper, but still that was something. So we modified a bit the design in January, and now it's totally immune to this kind of attack. So if you read the paper for at least the first 2 or 3 pages, it's really, really good. Second one, about 1 month later, it's maybe even more complicated. It's a bit shorter, but they consider a new metric. So when you try to compute how hard it is for an attacker, you want to find how expensive it is. So this notion of expensive, you formalize it by using some formal notion, some mathematical notion. So what we used to do is to consider the AT metric, which is essentially the time multiplied by the space. The point was that there would be a more realistic metric, which was the energy consumption, to make it very short. So based on this observation, they tried to find new attack, asymptotic attacks, so which are attacks on the design, as a function of its size, but not on specific instances. Okay. So I won't bore you with the mathematical details. It's pretty difficult to follow. But their point was that if you see it as a mathematical object, asymptotically for very high values of the parameters, there are some attacks that may be better than what we know. Okay. Conclusion, it doesn't matter in practice. It's theoretically interesting, but there's no impact on the actual hash. Okay. So I'm almost done. So I convinced you that Argon2 is so good. So we tried to convince people at the IRTF who are running the standardization process for ITF. There's an internet draft that is out. Here you can check it out. And one of the goals is probably to make an RFC of Argon2 to give it a more official status and to encourage people to use it. So I don't really know what is NIST's position at the moment. I understood that they have maybe other priorities, but I don't exclude that at some point NIST may decide to include Argon2 as a federal standard. All right. So short conclusions. Argon2 is the best password hash in the world, if you will. We understand well where it's good, where it's better than the previous approaches, and we understand its limitations, for example, side channel attacks. Now we can check out the code on GitHub. It's production ready. And you also have bindings for any languages, so you can use in any application you want. If you have any question, any pull request, anything you'd like to discuss with us, you can either send me an email directly or even better, register to the mailing list and email the mailing list. Thank you very much.
That easy, but still there might be questions for JP. Yeah. Raise your hands.
You mentioned the implementation was optimized for x86 architecture. I'm thinking of putting it into apps running on phone devices, which would be more ARM architecture. Any research or looking at how well that would work, or is it still the recommended choice in that situation?
So the question is about is it worthwhile to look at ARM implementations of Argon2? Actually, the implementation is just C89. We don't have assembly implementations, neither for ARM or for other architectures. It should compile on ARMS. I don't know if it's worth the effort of ARM optimizations. I'm really not sure. Maybe you want to discuss this with us.
So if I interpreted you correctly, in a situation where you have a network logon and a malicious attacker monitoring the traffic and doing timing attacks, would that be a situation where the Argon2i is a better choice of algorithm?
Okay, so the question is essentially if remote timing attacks are possible on Argon2. Well, we've seen that on other pieces of software, timing attacks that were assumed to be only feasible locally turn out to be feasible remotely. So I would not make any claim on the resistance to remote timing attacks, and you should probably go with Argon2i then.
More questions? Oh, Jeff, come on. Yeah. Okay. Well. Okay. Okay. Well, you were late, Jeff. So
Yeah.
I'll first.
So, have you made any effort to get this into some of the common key password manager programs, particularly KeyPass, which is an open source
So
project?
Try to push it in popular password managers. We did not. Maybe we will.
Yeah, well, we can give that question to. We have Jeff Goldberg from AgileBits, producers of 1Password, in the audience. So Jeff, yeah, you can give him an applause as well. That's okay. Jeff, Argon2 in 1Password, please.
Well, we've got. I mean, we'd love to, obviously, but some of the clients that we use, there's just no way to get it in there yet. We're still dependent on PBKDF2.
Yeah.
Just given the particular platform.
Okay, I'll stop using 1Password and go for a keep. I'm kidding.
So I have to admit that. But actually, my question was kind of for all of those people who said that they were familiar with Argon2 and not using it, is kind of why. You know, are they in the same position that I'm in? We've got one platform where we need to do it in JavaScript.
Right. Well, I guess they heard about it, but they don't get to choose that password hash.
Okay.
Yeah.
So I guess this is more of a statement than a question, but you know, I wasn't using Argon2 a year ago because I didn't really like the code. Yeah. I didn't know that you'd done a sort of a re-implementation of it, so that's great. But you know, Argon2 is highly tunable, so why don't you just tune down the memory parameters a little bit, and it should still be strictly superior to you know, the password-based key derivation function. Yeah, whatever.
It's easier to pronounce than.
Yeah, sure. So, you know, just tune the parameters down, and it should be a viable replacement.
Yeah.
More questions? None. One.
No. So.
I was just going to say, it should be a replacement just because it's quicker to say.
Steve. There you go.
So you said that script can't be, well, script can't be slowed down.
Yeah, I know what you're going to ask.
P parameter.
P parameter, yeah. But it makes it slower, but it increases the parallelism. So if you don't want to be more parallel, if you want to be fully serial, if you just... I mean, P is a parallelism, so if it's larger, then you can parallelize it even better than...
Well, all it does, so the way P works is so you have the setting for however much memory.
Yeah.
Then that like block
Yeah.
is just repeated multiple times. You can do them sequentially or all at the same time with more memory, obviously.
Yeah.
But it is a way to make it slower.
Okay. Yeah. But it's not clear from the
Yes,
specification.
it is very not clear.
Yeah.
Because, you know,
Thanks for correcting me.
Okay. More questions? Well, then I would just say thank you, JP.
No, thank you, Per. Thank you.